In many industrial applications, we wish to have the output of a system go to a desired value, or perhaps follow a desired trajectory. So, we want y of t, the output of this system, to be some desired signal, which will denote y desired of t. So the question is, how to make the input do the appropriate signal so as to make the output act like the desired signal? How should the input be chosen so that this will occur? If the input is chosen without measuring the output, y of t, then this is open loop control. If the input is chosen with a measurement of the output, y of t, then this is feedback control, which we'll discuss in a later lecture. Now let's focus on open loop control. We looked at open loop control once before when we examined the gantry crane problem. If you recall, in that problem, we had to pick the input, which was the velocity profile, so as to get a good behavior on the swing of the load. Now let's look at the problem more generically. How do we pick x such that the output y is the desired signal? We can choose x to make the output the desired output simply by solving a mathematical problem. Let's look at an example to illustrate. Let's suppose the system is governed by the differential equation shown at the top of the page here. And let's suppose that we have a desired signal that is 1 minus e to the minus 6t u of t. We want our output to be equal to this desired signal, and we want to pick x of t to make it so. So let's plug in y of t is equal to y desired of t, the expression given, and solve the equation for x of t. So plugging y desired of t into our differential equation, we'll find that y dot is the first term in the brackets at the bottom of the page, and that y of t, of course, is y desired of t. When we take the time derivative of y desired for the first term, we'll get two terms by the product rule. The first term will be 1 minus e to the minus 6t multiplied by the Dirac delta, since the Dirac delta is the derivative of u of t. And the second term will be the derivative of 1 minus e to the minus 6t multiplied by u of t. Now from the sampling property of the Dirac delta function, we know that the quantity 1 minus e to the minus 6t delta of t is equal to 0. We now do a little bit of algebra, simplify, and solve for x of t. So the input that will make the output y desired of t will be x of t equals 2 plus 4 e to the minus 6t times u of t. We've just demonstrated a method of open loop control. We find the input that makes the output the desired signal without actually measuring the output. Just solve for this input, doing all our work in the time domain using the differential equation. But we could have done it all in the frequency domain, and that's what I'll show you here on this slide. So, we have a relationship between the input, x of s, and the output, y of s, that relationship being the transfer function. And we can find this transfer function from the differential equation. It is 1 over s plus 2. We can take the Laplace transform of y desired of t to find y desired of s. And if we do that, we'll find that's 6 over s times s plus 6. Now we can plug both y desired and the transfer function 1 over s plus 2 into the expression y of s equals g of s times x of s, and then simply solve for x of s, which will be the Laplace transform of the signal which will create the desired output. Solving for x of s, we find x of s is quantity s plus 2 divided by 1 multiplied by 6 over s times s plus 6. Now I deliberately wrote x of s in this fashion because I wanted you to see something. The s plus 2 divided by 1 is 1 over g of s. the transfer function between the input and the output. This 1 over g of s can be thought of as the inverse of the system. So when we multiply the inverse of the system by the desired output, we'll find the input that creates this desired output. All that remains now is to inverse Laplace transform x of s to find x of t. Working in the frequency domain like this gives you a little bit more understanding of how open loop control works. It will also indicate to us, with a little bit more analysis, exactly why open loop control does not always work in practice. There are two problems. Both these problems relate to the fact that our model of the system is not the actual system. There's two aspects to this. First, our model is not going to be perfectly accurate, no matter how much time we spend in modeling. Partly because we won't be able to model things perfectly, and partly because things tend to change. Even if we have the correct model today, then tomorrow or the day after, the system will behave somewhat differently. And this inhibits our ability to invert the dynamics, to cancel things out. So we need to know what the system's dynamics are in order to cancel them correctly. The second problem with our model is it doesn't show any other inputs to the system, and typically there are other inputs that will act on any system. And these inputs will have an effect on the output, y of t, and will make it different than y desired of t, even if our model could be perfectly inverted and was perfectly known. Let's illustrate the first of these two problems by going back to our example. Let's suppose the actual system was governed by the differential equation at the top of this page. Note this is a different differential equation than we had before. The previous differential equation will consider our model of the system. Our model does not represent the actual system. They have different differential equations. Nevertheless, our model is used in finding the transfer function g of s and in trying to invert the dynamics. We pick our input on the basis of this model, so our input is the same as before. It will be in the frequency domain s plus 2 divided by 1 multiplied by 6 over s times s plus 6. Our input is based upon the model. Now that input goes into the transfer function of the actual system, which is obtained from the differential equation at the top of this page. The output in response to the input we have chosen by open loop control is given in the frequency domain by the expression shown in the middle of the page. And what you'll notice here is we have a multiplication of the actual system's transfer function, which is 0.8 over s plus 3, times 1 over the model g of s. That would be s plus 2 divided by 1. You'll note that g actual multiplied by 1 over g of s does not cancel out to make 1, since g actual is not equal to g. As a result, y of s will not be equal to y desired of s, and so the actual system output, y of t, will not be the desired system output. I'll now introduce an example where both open loop control and feedback control have been used. Our example is a continuous fryer for cooking potato chips. Potato slices are dumped into a bath of hot oil at one end of the continuous fryer. They're submerged and transported by a belt underneath the boiling oil. They move along for a period of time until they're cooked, where they're carried out of the fryer on a conveyor belt. It is critical to this manufacturing process that the chips come out appropriately cooked. If they spend too little time in the oil, they will not be crisp, and if they spend too much time in the oil, they will be burnt. The amount of time that they spend in the oil is controlled by the speed of the belt. The process control problem is one of controlling the belt speed so that the chips come out appropriately cooked, that is, crisp but not burnt. This problem is difficult because the raw potato slices do not always enter the vat with the same moisture level or the same temperature, and the amount of cooking necessary for the potato slices is dependent upon their moisture and temperature initially. Viewing this problem from a systems point of view, we can see that the chips entering have a certain moisture content, and that the goal of cooking is to reduce this moisture content to a certain level. If the chips are cooked too long, the moisture content is reduced too much, and the chips will be burnt. The independent variable that we control so as to control the moisture content of the chips leaving the fryer is the belt speed. So we can think of the input to this system as the belt speed, and we can think of the output as the moisture content of the chips leaving the fryer. Clearly, this input, the belt speed, has an effect upon the moisture content of the chips coming out, that is, the output of the system. Let's suppose we look at the moisture content of a chip coming out of the fryer at the present time. This moisture content will depend upon how long this chip has spent in the fryer. And how long it's spent in the fryer is not a function of just the current belt speed, but a function of the belt speed for some period of time. That is, this system is a dynamic system, not an instantaneous system. In open loop control, we would fix the belt speed to some nominal value that would seem to give a good moisture content to the chips coming out for typical values of the moisture content and temperature of the potato slices entering. Choosing the belt speed in this fashion would depend upon us knowing exactly what temperature the oil was inside the bath. If the temperature varied, that would amount to changing the transfer function of the system between belt speed and moisture content. This is a problem of the inexact cancellation we referred to earlier. We pick the belt speed on the basis of a model of the fryer system. If the actual system differs from the model, then we do not achieve the desired output. For example, suppose a typical potato slice has a moisture content of 32%. If the temperature of the oil was 280 degrees, it would take approximately 2 minutes and 40 seconds to achieve a proper potato chip. But if the oil was 260 degrees, it would take approximately 3.5 minutes to achieve crispness. If the belt speed was set to be proper for 280 degrees and the actual oil temperature was 260 degrees, then after 2 minutes and 40 seconds, the potato chip would not be fully cooked. A second problem of modeling has to do with the moisture content of the potato slices entering. Depending upon the time of year and the source, the slices entering may have different moisture content. This variation in moisture content would not be significant within a batch of potatoes, but might vary from one delivery to another of the raw material. A typical slice entering might have a moisture content initially of 32% and might require 2 minutes and 40 seconds to achieve proper crispness. However, another day, the slices entering might have a moisture content of 30% and only require 2 minutes and 10 seconds to achieve crispness. Choosing the belt speed in an open loop fashion, without looking at the moisture content of the chips coming out of the machine, is complicated due to these variations. It's difficult to achieve proper crispness when the system might vary over time. We will discuss feedback control in detail in our next lecture, but for now let's briefly talk about how feedback control might be used to pick the belt speed for the continuous fryer. In feedback control, one would measure the moisture content of the chips coming out of the fryer. One would adjust the belt speed so as to bring the moisture content of the chips leaving the fryer to the desired value. The advantages of feedback control for this problem should be apparent to you. We'll be able to get a good potato chip coming out in spite of variations in the potato slices entering the fryer, because the belt speed will be appropriately adjusted so as to compensate for the variations in the initial moisture content and temperature of the slices entering. All this talk of potatoes brings back childhood memories of working on the family farm with my brother Gustav in northeast Minnesota. Somehow my parents knew that I just wasn't cut out for farm life.